Hello, welcome back to Precalculus. Today we'll be diving into section 1.3, rates of change and behavior of graphs. If you don't know what calculus is informally called the math of change. A lot of things changing in calculus. This is your first real intro to that. This section answers questions like, how fast is something changing, and is my function going up, down, or staying constant? We'll also go over how to calculate the rate of change, which is just fancy talk for slope. The rate of change tells you how much y changes for a given change in x. We usually call this the average rate of change. And the formula for average rate of change is delta y over delta x, where delta means change in. Change in. So your rate of change is the change in y over the change in x. A better way to write that out would be y2 minus y1 over x2 minus x1, something I'm sure you've all seen before. The more formal way to write this in terms of precalculus, though, would be f of x2 minus f of x1 over x2 minus x1. It's the same thing, it's just written in function notation instead of using y. Don't get too scared away by the notation and the new name for it. It's literally just slope, the same one you used back in Algebra 1. For our first example, we're asked to find the average rate of change, that's what AROC means, of f of x equals 2x squared minus 3x plus 1, from x equals 1 to x equals 4. This part might seem a little new. We're not really used to doing things like this, but let me show you intuitively what that means. Let's take this arbitrary graph. This obviously is not the function listed here. It's just some arbitrary curve. And we have the points marked out at x equals 1 and x equals 4. Let's put a point on the graph at x equals 1 and a point at x equals 4. Now we draw a straight line between those 2 points. This line is called a secant line. What we're trying to find is the average rate of change between these 2 points on that curve. And that average rate of change just so happens to be the slope of this secant line. So we know, based on this graph, we have an x2 and we have an x1. Now we need a y2, which would be somewhere around here, and a y1, which would be somewhere around here. How would we find y2 and y1? Well, let's plug in x2 and x1 into our equation. So let's label our x2 and our x1. This is x2, this is x1. Now let's plug them in individually to find two ordered pairs. Let's start with f of 1. F of 1 would equal 2 times 1 squared minus 3 times 1 plus 1. This is just 2. This is 3, and this is 1. 2 minus 3 is negative 1, plus 1 equals 0. So we know when our input is 1, our output is 0, so we're left with the ordered pair 1, 0. Now let's plug in 4. F of 4 equals 2 times 4 squared minus 3 times 4 plus 1. This will give us 32. This will give us 12, and this will give us 1. This gives us 20 plus 1, or 21. So when our input is 4, our output is 21. So we have an ordered pair, 4, 21. Now this is perfect. We have a y1 and an x1, along with a y2 and an x2. So now we have everything we need for our average rate of change formula. So let's plug it in. y2 minus y1 over x2 minus x1. This gives us 21 over 3, or 7. That means the slope of this secant line, obviously not this one, it's not drawn to scale, it's not the same function, but the slope of our secant line between x equals 1 and x equals 4 is 7. That is our slope. You can write it like this, m secant. It's the slope of our secant line. That means for every 1 unit increase in x, so when x increases by 1, y goes up by 7 on average between x equals 1 and x equals 4. Remember, if you actually plotted this graph of this function, you would not obviously get a slope of 7 over the whole graph. but on average between those 2 points, your slope is going to be 7. I know this whole section seems a little redundant, but please stick with me here. After we get through this little paragraph, we're going to go and see some examples of all this in action. But you have to understand these core ideas. A function is increasing when the graph goes up as you move right, going in this general direction. A function is decreasing when the graph goes down as you move right, so this general direction. A function is constant when it stays flat as you go right, so you would just be a straight line all the way to the right. That is constant. But let's see some examples of this in play. Let's take a look at the function negative x squared plus 4. I've taken the courtesy to draw this function out for you so it becomes a little more intuitive. Let's think about the shape a lot here. From left to right, starting at the leftmost point, as you go to the right, you're going up and up and up and up and up until this point right here. So from negative infinity all the way up to 0, you're increasing. Your graph is increasing. Not including 0, because at 0, you can't really find a slope there. You can say here the slope is pretty definitely positive, even though you don't know what the slope is, you can safely say it's positive. At 0, you don't really know what the slope is. However, if we start at 0 and go down towards the right, you can see as we go to the right, we go down very far. So from 0 to positive infinity, you can say safely that it is decreasing. So let's write this out a little more formally. We'll say it's increasing from negative infinity to 0, and it's decreasing from 0 to positive infinity. Pretty straightforward, right? Let's take a look at this slightly more thought-provoking example. A car travels 60 miles in 1 hour and 150 miles in 3 hours. What's its average rate of change? Well, first, let's try to think of this in terms that we know, in terms of a function. Let's say when your x equals 1, your y equals 60, right? You plug in 1 hour, you see they drove 60 miles. What happens if you plug in 3 hours? Well, they give that to us. When x equals 3, our hours, y equals 150, our miles. So now we have a clear x1, y1, and a clear x2, y2. Let's just use this to find the average rate of change. Now that we have our variables laid out, let's just do the formula to find average rate of change. So you have y2 minus y1 over x2 minus x1. That gives us 90 over 2, which gives us 45 miles per hour. Now remember, this is not saying that the person drove 45 miles per hour the whole trip, but it's saying on average that person did drive 45 miles per hour. You'll also hear about end behavior. End behavior is what the graph does as x goes to positive infinity or negative infinity. There is a good little system for finding end behavior of polynomials based on the degree of the leading term and the coefficient of the leading term. Let's think about functions that have an even degree, like y equals x squared. Well, the graph of this goes up as you go to negative infinity and up as you go to positive infinity, right? As x increases forever and ever, y increases forever and ever. As x decreases forever and ever, y still increases forever and ever. So if your function has an even degree leading term, you're going to go up forever and ever on both sides. However, don't think of it as when I have an even degree, it will always go up. What I want you to think of it as is that it'll go in the same direction on the left as it will on the right. You'll see why in a moment. Let's think about functions that have an odd degree, like y equals x, right? Just x to the first power. That's an odd power. Y equals x looks like this, right? It goes up forever as you go to the right forever, and it goes down forever as you go to the left forever. So you can see it does not do the same thing like our even degree does. Our even degree goes up on the left and up on the right. Our odd degree goes down on the left and up on the right. Now, our leading coefficient tells us what the right side is going to do. Ignore the left. It tells us only what the right side is going to do. If you have a positive leading coefficient, the right side will go up. If you have a negative leading coefficient, the right side will go down. Let's try to combine some of these ideas together in some examples. For example, we have f of x equals negative 7x cubed plus 2x squared minus 5x plus 3. When it comes to our behavior, we don't care about any of this over here. What we care about is our term with the highest power. Not always will this term be the first term. You may have to reorder your polynomial. Just make sure you look for the term that has the highest power. Now, let's look at its degree. We have our degree is 3. With degree 3, it'll do something different on the left side of the x-axis as it will on the right side. So now let's find out what it does on the right side. We know on the right side, since this leading coefficient is negative, that it's going to go down on the right. So if it's going to go down on the right, that has to go up on the left, right? Because we know it goes in two different directions on the left and right of the x-axis. That is your end behavior. This will work for negative 7x to the 5th or negative 7x to the 11th as long as that degree is odd and that leading coefficient is negative. I hope you get the gist of this by now because it's a pretty simple concept. I would strongly encourage you to try to memorize these, but do remember, this won't help you for finding the end behavior of every function, just polynomials. In summary, the average rate of change is f of x2 minus f of x1 over x2 minus x1. When you have a positive slope for your secant line, your function is increasing. When you have a negative slope for your secant line, your function is decreasing. When you have a zero slope for your secant line, your function is constant. And in real-world problems, your slope is your rate, the rate at which something changes. Or in the case of math, this rate is the rate at which y changes with respect to x. Before I go, I have a few practice problems I'd like you to try. Here are your two practice problems. I would like you to give them a shot, or I will give you the answers and work in 3, 2, 1. This is all the answers and work. My tutoring email is in the description. Thank you for watching, and I'll see you next time for Precalculus 1.4.